All right, hello, how is everybody doing out there? Welcome to my channel. This is an educational channel, and we do deep dives on great theories of everything from the past, ancient and modern, and we try to go into every aspect and help you to figure out how to use them to shift your paradigm, to awaken a 5D consciousness, to fill out your holistic worldview. Today is our 502nd video on the reciprocal system of theory from Dewey B. Larson. And Mr. Larson was an American engineer who lived in the 20th century. He died back in 1990, but not before putting out a dozen or so books, many articles and talks. He had a journal going for a while that published a lot of his associates as well. And in 1959, he put out his two fundamental postulates about how he believed the universe operated. And then from there, he derived a theoretical universe of what his universe would look like if his postulates were correct. He then compared his theoretical universe with the actual so-called empirical universe of the modern legacy scientists who have done many laboratory experiments and had published all these results in their scientific tables. So Larson would compare he'd come up with equations for various things and compare his results that were derived theoretically with the laboratory results from the legacy scientists. We are looking at one of those books today called Basic Properties of Matter, primarily on chemistry. And, in this book, Larson goes into some of the basic properties of matter, like the melting point or the compressibility, and then, explains his findings, why they, in many cases, recreate the scientific tables, and in other cases, maybe disagree with the scientific tables, and so on. Today we are in the middle of chapter 17, which is on ionization. And Larson's reciprocal system is also known as a universe of motion, which is the name of one of his books on astronomy. Larson was one of the few scientists to propose a universe based entirely on motion. The universe is made out of motion in Larson's system. And he stood out from some of his predecessors because he defined motion as the relationship between space and time, pointing to a reciprocal relationship between space and time. Larson's first postulate states that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And then he goes from there. The second postulate really has to do with the kind of the background that he applies his first postulate to, stating that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. So Larson uses math, geometry, and logic to derive his theoretical universe from that first postulate. And if you want to get further into the reciprocal system, you probably want to watch one of my first 474 videos on this subject that I have done on this channel. For now, I'm going to more or less assume that you have some working background in the reciprocal system to continue, because we're reading from his book, and it just takes a long time to explain the reciprocal system in enough detail to get you up to speed. And I'd like to get through this book here, so to move a little bit faster. And so we're going to start right here in the middle of chapter 17, ionization. While the discovery of the positron solved one of the symmetry problems, it produced another that has been even more troublesome. Inasmuch as the electron and the positron are inversely related, so far as we can tell, it would seem that they should appear in equal numbers. But positrons are scarce in our environment, whereas electrons are plentiful. Conventional science has no answer to this problem, other than mere speculations. From the theory of the universe of motion, we find that the asymmetrical distribution of electrons and positrons, and of positive asterisk and negative asterisk charges in general, is not due to any inherent difference in the character of the motions that constitute the charges, but is a consequence of the fact that the net rotational displacement of the atoms of ordinary matter is in time. That is, it is positive. The charges acquired by these atoms in the ionization process are therefore positive, except in the relatively few instances where negative, that positive has an asterisk, which denotes the conventional usage as opposed to his findings. So, except in the relatively few instances where negative asterisk ionization is possible because of the existence of negative electric rotational displacement of the appropriate magnitude in the structures of certain atoms. The simple positively asterisk charged subatomic particles, the positrons, are scarce in the vicinity of material atoms because their net rotational time displacement is compatible with the basic structure of the atoms, and they are readily absorbed on contact. The corresponding negatively asterisk charged particles of the material system, the electrons, are abundant, as their space displacement is stable in the structures of the material atoms only to a very limited degree. It is evident that both of the mechanisms discussed in the foregoing pages, the selective incorporation of the positrons into the structure of matter, which leaves a surplus of free electrons, and the ionization mechanism, which produces only positive ions, asterisk ions, under high temperature conditions where most of the ionization takes place, are incompatible with the existence of a law requiring absolute conservation of charge. This will no doubt disturb many individuals because the conservation laws are generally regarded as firmly established basic physical principles. Some consideration of this issue will therefore be appropriate before moving on to other subject matter. In conventional physical science, the conservation laws are empirical. As expressed by one physicist, quote, "We are in a curious situation. We know the conservation laws, but we do not know their underlying dynamic basis. That is, we do not know the kind of symmetries responsible for them." End quote. While the conservation laws have retained their original status as important fundamental principles of physics during the broad expansion of scientific knowledge that has taken place in the 20th century. The general understanding of their nature has undergone a significant change. Any empirically based relation or conclusion is always subject to modification by reason of relevant new discoveries. This is what has happened to conservation. Originally, the law of conservation of energy, for instance, was thought to be inviolable. No gain or loss of energy has ever been observed in an isolated system, says a 1919 textbook. This statement is no longer true. Mass and energy, we have found, are interconvertible. Thus, one can increase at the expense of the other. The content of a conservation law has therefore had to be redefined. As expressed by Eric M. Rogers, quote, "In its present fullest form, you may consider it, the conservation of energy, more than a generalization from experiment. It has expanded into a convention, an agreed scheme of energy now so defined that its total must, by definition, remain constant." It is now frequently stated that we should not speak of the conservation of mass or the conservation of energy, only the conservation of mass energy. However, the conversion of one of these entities into the other occurs only under circumstances that, in the terrestrial environment, are quite exceptional, and the separate conservation laws are applicable under all ordinary circumstances. It would seem more appropriate, therefore, to state these laws individually, as in the past, and to qualify the statements in such a way as to limit the application of the laws to situations in which there is no conversion to or from a different form of motion. These same considerations apply to electric charges. There is a wide range of physical activity in which the conservation of charge is maintained. Indeed, the current prevailing view is that charge conservation is absolute, as indicated in the following statement. Quote, "The law of conservation of electric charge states that there is no way to alter to the slightest degree the total amount of electric charge in the world." End quote. Our finding is that all physical quantities with the dimensions T over S, including electric charge, are equivalent to and, under appropriate conditions, interconvertible with kinetic energy. Thus, while energy and charge are each conserved individually within a certain range of physical processes, there is a wider range of processes in which the quantity T over S is conserved, but changes occur in the magnitudes of the subsidiary quantities, such as charge or kinetic energy, because of conversion from one to another. The law of conservation of electric charge is valid wherever no such conversion takes place, and it has persisted because most of the common electrical processes are of this nature. The observation that has been most influential in leading to the conclusion that charge conservation is absolute is the existence of processes in which positive and negative charges are created in pairs and destroyed jointly. A unit negative charge is a unit of outward scalar, negative with an asterisk, is a unit of outward scalar motion in time. A unit positive asterisk charge is a unit of outward scalar motion in space. Since the two motions are oppositely directed from the natural 0 point, a combination of the two units arrives at a net total motion, measured as energy or speed, of 0 on the natural scale. Thus, the creation or neutralization of such a pair of charges involves no change in the total net charge or energy. It is another instance of what we have called a zero energy process. The induction process, discussed in chapter 16, is another example. As explained there, an external positive asterisk charge induces a rotational vibration or charge, which is positive asterisk relative to each of the atoms of the object subjected to the charge, and negative asterisk relative to the mobile units of space, the electrons, in which some of these atoms are located. The attractive and repulsive forces due to the external charge then cause each of the atom electron combinations to separate into a pair of positively and negatively charged entities. It can be seen that this process does not alter the net amount of electric charge. An object, a combination of motions, with 0 net rotational vibration or charge, separates into 2 components, the net total charge of which is 0. However, it is also evident that these are processes of a special kind, and the fact that charge is conserved in such processes does not indicate that charge is always conserved. The best resolution of the conservation question appears to be to recognize that each of the conservation laws previously formulated is valid within certain limits, and therefore has a specific kind of usefulness. But to state each of these laws in such a form that its applicability is restricted to the range of conditions in which no conversion from or to other forms of motion is involved. While the foregoing is a significant limitation of the field of applicability of the charge conservation law, there is still a wide range of physical phenomena in which electric charge is conserved, as the processes that involve changes in the net total T over S in the form of electric charge are confined mainly to those that take place at very high temperatures or very large kinetic energies. One of the important areas in which charge is conserved is ionization in liquids. The molecules of a simple chemical compound such as hydrochloric acid, HCl, for example, consists of 2 components, in this case a hydrogen atom and a chlorine atom, oriented in the manner described in Volume 1 and held together by the cohesive forces described in Chapter 1 of this volume. In the liquid state, the molecules move independently, subject to the restrictions imposed by the nature of this state of matter. The effective rotation of the hydrogen atom, as oriented in HCl, is positive, while that of the chlorine atom is negative. These components of the molecule are therefore capable of taking positive asterisk and negative asterisk charges, respectively, if they separate. The molecules in a liquid aggregate are in constant motion, and collisions are frequent. A certain percentage of these collisions, depending on the temperature, are energetic enough to break the bonds between the molecular components and separate each molecule into 2 parts. Ordinarily, these parts recombine promptly, but if the atom is located in a unit of electron space, the collision imparts a rotational vibration to each of the components. As noted in Chapter 13, such rotational vibrations, electric charges, are easily produced in contacts of various kinds. This rotational vibration is a positive asterisk motion of the hydrogen atom relative to the associated electron space, and a negative asterisk motion of the electron relative to the chlorine atom. The generation of the charges is thus a zero energy process, and it does not add to the energy of the system. The HCl molecule now has become an H plus molecule, an ion, and a Cl atom associated with a charged electron, a Cl negative ion, we may say. The charges on these new molecules, or ions, balance the valences of their associated atoms, and the ions are therefore stable in the same sense as the original HCl molecules, except that there is a rather strong tendency toward recombination that limits the net amount of ionization. Let us now turn to an examination of the effects that are produced when a voltage is applied in such a way as to cause a voltage gradient in a liquid that is, to some extent, ionized. This is accomplished by inserting two electrical conductors, or electrodes, into the liquid and connecting them through a source of current so that the electrons are withdrawn from the positive asterisk electrode, the anode, and forced into the negative asterisk electrode, the cathode. Liquids such as HCl are not conductors of electricity in the sense in which this term is applied to metals. That is, they do not permit free movement of electrons. However, the introduction of a voltage differential causes a movement of the ions in the ionized liquid. As we saw in Chapter 15, this voltage differential forces some of the electrons at the cathode out into the spatial equivalent of time and withdraws a similar number of electrons from the spatial equivalent of time at the anode. Some of the contacts with liquid molecules are sufficiently energetic to impart charges to electrons in the vicinity of the cathode. Thus, a quantity of negative asterisk charge accumulates in the liquid in this vicinity, a process known as polarization. At the anode, the withdrawal of electrons leaves a deficiency of electrons relative to the equilibrium concentration. This leads to a breakup of some of the neutral combinations of positive asterisk atoms and negative asterisk electrons. The electrons thus released are absorbed into the electron vacuum, losing their charges in the process. This leaves a surplus of positively asterisk charged ions. That is, the region in the vicinity of the anode is positively asterisk polarized. As a result of the polarization, the positive asterisk and negative asterisk ions are attracted to the cathode and anode, respectively, by the electric forces between unlike charges. The positive asterisk ions, such as H+, arriving at the cathode, neutralize negatively charged charged electrons and withdraw them from the electron concentration in equivalent space. These are replaced by electrons drawn from the cathode. Additional electrons then acquire charges by the collision process to restore the polarization equilibrium in the liquid surrounding the cathode. Meanwhile, the negative asterisk ions, such as Cl-, arriving at the anode, neutralize positive asterisk charges in the vicinity of that electrode and release electrons which are drawn into the anode to restore the polarization equilibrium. The loss of electrons from the cathode and acquisition of electrons by the anode in the process that has been described creates a voltage difference between the two electrodes in addition to that supplied by the external voltage source. A current therefore flows from the anode to the cathode through the metallic conductor to restore the equilibrium condition. This current persists as long as the ions continue to move through the liquid. The proportion of the total number of molecules that will be ionized in a particular liquid under specified conditions is a probability function, the value of which depends on a number of factors, including the strength of the chemical bond, the nature of other substances present in the liquid, the temperature, etc. Where the bond is strong, as in the organic compounds, the molecules often do not ionize at all within the range of temperature in which the substance is liquid. Substances such as the metals, in which the atoms are joined by positive bonds, likewise cannot be ionized in the liquid state, since the zero-energy ionization process depends on the existence of a positive * negative * combination. The presence or absence of ions in the liquid is an important factor in many physical and chemical phenomena, and for that reason, chemical compounds are often classified on the basis of their behavior in this respect as polar or nonpolar, electrolytes or non-electrolytes, etc. This distinction is not as fundamental as it might appear, as the difference in behavior is merely a reflection of the relative bond strength, whether it is greater or less than the amount necessary to prevent ionization. The position of organic compounds in general as non-electrolytes is primarily due to the extra strength of two-dimensional bonds characteristic of these compounds. It is worth noting in this connection that organic compounds such as the acids, which have one atom or group less strongly attached than is normal in the organic division, are frequently subject to an appreciable degree of ionization. Ionization of a liquid is not a process that continues to completion. It is a dynamic equilibrium similar to that which exists in between liquid and vapor. The electric force of attraction between unlike ions is always present, and if an ion encounters one of the opposite polarity at a time when its thermal energy is below the ionizing level, recombination will occur. The elimination of ions is offset by the ionization of additional molecules whose energy reaches the ionizing level. If conditions are stable, an equilibrium is reached at a point where the rate of formation of new ions is equal to the rate of recombination. The conventional explanation of the ionization process is that it consists of a transfer of electrons from one atom or group of atoms to another, thus causing a deficiency of electrons, identified as a positive * charge, in one of the participants, and an excess of electrons, identified as a negative * charge, in the other. In the electrolytic process, the negative ions are assumed to carry electrons to the anode, where they leave the ions, enter the conductor, and flow through the external circuit to the cathode. There they encounter the positive * ions that have been drawn to this electrode, and the charges are neutralized, restoring the electrical balance. This is a simple and plausible explanation. It is not surprising, therefore, that it is met with widespread acceptance. Like many other attractive but erroneous hypotheses, however, its net effect has been to direct physical thinking into unproductive channels. In fact, this interpretation of the electrolytic process is one of the major influences contributing to the belief that the electric current is a movement of charges, one of the basic errors of present-day electrical theory. Since negative * charges clearly do move through the electrolyte to the anode, there is, on first consideration, an analogy with the metallic circuit, and discussions of electrolysis habitually refer to, quote, passing a direct current through an electrolytic solution, end quote. If there actually were a continuous flow around the circuit, and if the moving units could be identified as negative * charges in one segment of that circuit, it would be reasonable to assume that the moving units in the remainder of the circuit are also charges. But this argument is wholly dependent on the continuity, and that continuity clearly does not exist. The electrolytic process is not a simple flow of current around the circuit. It is a more complex series of events in which both positive asterisk and negative asterisk charges originate in the solution and move in opposite directions to the electrodes. This means that electrolytic conduction has to be explained independently of metallic conduction, and it eliminates most of the support that the electrolytic process has been presumed to give to the conventional theory of the electric circuit. The final topic for consideration in this chapter is the overall limit on the magnitude of the combined thermal and ionization energy. As pointed out earlier, the thermal energy must reach a certain level, which depends on the characteristics of the atoms involved, before thermal ionization is possible. After this level is reached, an equilibrium is established between the temperature and the degree of ionization. A further increase in the temperature of an aggregate causes both the linear speed displacement, the particle speed, and the charge displacement, the ionization, to increase, up to the point at which all the elements in the aggregate are fully ionized. That is, they have the maximum number of positive asterisk charges that they are capable of acquiring. Beyond this point of maximum ionization, a further increase in the temperature affects only the particle speeds. Ultimately, the total of the outward displacements, ionization and thermal, reaches equality with one of the inward magnetic rotational displacement units of the atom. The inverse speed displacements then cancel each other, and the rotational motions that are involved revert to the linear status. At this point, the material aggregate has reached what we may call a destructive limit. Okay, we're going to leave it right there. There's a few more pages to go in this chapter, but we're not going to finish it here today. So just keep in mind we're discussing chemistry, but we're really, discussing a theory of everything. And, we're just trying to get the context and how you apply this theory of everything so that you can learn to apply it to whatever subject you'd like. Chemistry is one of many different topics that Larson tackled, and we're trying to get a broad view of that, all the different topics, so that we can see how the reciprocal system can be applied. And thanks for tuning in today. Have a great day.